Hello everyone, MKS here. This session going to be very challenging. Thrilling for you because the topic we are going to do today is known as electric flux and Gauss law. Maybe you will not be able to complete the topic today, but the concept of electric flux we'll try to understand throughout the discussion. And it has so many applications in electrostatics, you won't believe. Many problems of electrostatics so far we have done by using integration, all those things can be made simpler if you have a good idea of electric flux and Gauss law. Without wasting time, let us start, and request for you stay tuned till the end of the session for better understanding of the topic. Electric field lines or electric lines of forces exhibit both qualitative and quantitative aspect because they represent the behavior of the electric field in a visual and mathematical manner. If I start writing everything the way I have written here before starting the class, then it will take long time. That's why to reduce the timing of the class, I have made this arrangement. So let us know what is qualitative nature of electric field lines. Electric field lines provide qualitative information about the electric field's direction and strength at different points in space. This we have seen in previous session. Key qualitative aspect of electric field lines include its direction. Electric field lines show the direction a positive test charge would experience a force if placed in the field. We did all these things, but let me remind you, they originate from positive charge, terminate on negative charges, including the direction of the electric field. Density. The density of electric field lines represent the strength of electric field. This part I have mentioned in the past session that if field lines are close to each other, then stronger field will be there. If they are further apart, it will signify a weaker field. And behavior near conductor. Electric field lines are perpendicular to the surface of conductors in electrostatic equilibrium. This you know that electric field lines are perpendicular to the surface of conductor in electrostatic equilibrium, and this will illustrate the Selling effect of conductors. This I will discuss again in future, that Selling effect of conductors. Let us know quantitative nature, which we are going to discuss today mainly. Electric field lines have quantitative significance as they can be used to calculate the electric field strength at different points. What is quantitative aspect of electric field? This will mention field strength, the density of field directly related to strength of electric field. In fact, electric field strength at a point is defined as number of field lines passing through unit area held in a direction perpendicular to direction of flow of electric lines of forces. This we have already discussed. Closer the lines, higher the electric field strength. Field intensity, spacing between field lines can be used to, this comes under quantitative nature also. Spacing between field lines can be used to determine electric field intensity. Denser concentration of lines indicate higher electric field intensity. The next part for quantitative nature is this, that is flux calculation. Electric field lines aid in calculating electric flux. What is flux then? It is actually total number of lines of forces passing through a surface. See, if you keep some unit area, just let me show you the example. These are the field lines created by a positive charge. You know, they are radially outward, and for negative charge they are radially inward. If we hold this surface area near the charge, you can see that more number of lines of forces passing through this surface. But if we hold the surface bit away from the charge, then we observe that less number of lines of forces passing through this surface. So what does it mean? That this means electric field is weaker at this point in compared to electric field when you hold the surface area at this point. So number of lines of forces passing through an area is related to electric field. Already we have discussed, I just remind you today. This is true for uniform electric field also, is it? Don't say yes. Because uniform electric field, the strength will remain the same at all points. Strength will not vary. It is represented by drawing equidistant parallel lines. So if we imagine that there is an area, the number of lines of forces passing through this area at this point or some distance away from it will be the same. It will not change. Its value going to be changed in this case where field is non-uniform. Now let us go for that quantification of electric field lines. We want to calculate field lines through a surface, not through this unit area only. If we keep some other area, I mean larger area, then how many lines of forces passing through it we want to calculate. Got it? So if the previous one is unit area, then as per definition, number of lines of forces passing through this area is electric field strength. If we make the area bigger, if we make this area bigger, then how many lines of forces passing through it? This can be done by unitary method only. Per unit area, it is E. So this E is the number of lines of forces passing through area of 1 meter square. Through 1 meter square, if number of field lines crossing be E, then through A meter square, some arbitrary area A we have kept here, through this how many lines of forces will be passing? That is E into A. We get it by unitary method only. This totality of number of lines of forces passing through the surface is called electric flux. So electric flux is given by phi equal to total number of lines of forces passing through a surface. What is its unit? E has unit, you know, Newton per coulomb. Area is in meter square. So unit of phi going to be Newton meter square per coulomb. Okay. This SI unit only you keep in your mind. Okay. So revision of electric field lines and how electric field strength helps to find the total number of lines of forces passing through a surface is understood. Really understood. You ask yourself, is it understood? Okay. Whether you have understood or not, this you can answer in the comment box in the following session. That is where I am telling that there is a uniform electric field and you have to calculate flux through this surface. How do I account for this? Again by unitary method, if this area is A, strength of electric field remains the same at all points. So phi will be equal to E into A. Okay. For uniform electric field, it's true that phi will be equal to E into A. But previously, if the area is too large, which we have considered, then field strength may not remain the same at all points. Flux calculation may go wrong. Isn't it? So right now you understand it for uniform electric field. This definition phi equal to E into a total number of lines of forces calculation will match for this exactly, that is phi equal to E into A. Total number of lines of forces passing through this area when you hold the area perpendicular to it. And perpendicular to it means perpendicular to the flow of lines of forces. Problem arises when the surface is not perpendicular. If this plane surface was inclined, then what will happen? I am going to discuss. We need electric flux formula, proper electric flux formula now. What is that? First, let us know what is electric flux used, that it will allow us to calculate total electric field passing through a given surface. It helps us understand how electric field interact with different types of surfaces, such as flat, curved or irregular, I mean closed surfaces. So before we do all these things, let us know something about different types of surfaces first. Let me explain different types of surfaces. See, in this diagram, this one and this one, they are plane surfaces. I mean perfectly flat sheet of paper or a tabletop I have taken here. They have no curve or bends and extend infinitely in all directions. So these two are representation of plane surface. Closed surface, like a solid sphere, like a ball. It has three-dimensional object. It's a three-dimensional object that you know x, y, z coordinate. You need to explain a point on the sphere or inside the sphere. Okay? And this surface will completely, surface means this outer surface, will completely enclose the space inside. There are no opening or boundaries on this surface, making it closed. So surface of sphere, surface of ellipse, those are going to be, I mean ellipsoid, better to say. When you make it solid, then it is ellipsoid. These are known as closed surfaces. What about curved surfaces? Picture a cylinder, such as can of soda. Surface of cylinder is curved but not closed. This one curved surface, this curved surface of cylinder is curved really, but it is not closed. With the length of cylinder, it extends up to infinity. Its curvature distinguishes it from a plane surface while still being different from a closed surface. Alright? This also can enclose within a finite lane, would enclose a volume. But this has curved surface as well as this one has a plane surface. This top is a plane surface. You know, this you can see. This one is a plane surface. And this one, the outer one, is a curved surface. Okay? Now, step by step, one by one, I'll tell you how to calculate total number of field lines passing through a surface when it is placed in a electric field. Maybe uniform, maybe non-uniform. So, we need a formula for electric flux which will allow us to calculate the total electric field passing through a given surface. And it will help us to understand how electric field interact with different surfaces. This I told you earlier for flat, curved and regular surface. So, if I have taken a surface area which is perpendicular to direction of flow of field lines, then as you have seen, if this makes an angle 90 degree, this angle 90 degree, okay, 90 degree, then if the strength of electric field is equal to A, and the area of this portion, this area, I'm talking about this area of this portion is equal to A, then electric flux is given by phi equal to E into A. This we have established by using unitary method, because E is the number of lines of forces passing through unit area. So over this area, number of lines of forces passing equal to E into A. But there is a problem when this plane surface becomes little bit inclined with the direction of electric field. I mean, little bit means not 90 degree, other than 90 degree. Then what is going to happen? Imagine this area held perpendicular to direction of flow of electric field lines. Then phi will be equal to what? Strength of electric field into area. But problem arises when the surface is little bit tilted. Okay? Then do you think same number of lines of forces will pass through this area also? Magnitude of area same. If this one A, this one is also A. But here, in this case, in the second position of the plane, less number of lines of forces will pass. In fact, this kind of area you have to take projection in a direction perpendicular. Suppose this one makes an angle theta with the direction of field line. I mean not 90 degree. In that case, you just consider that this angle is theta here. Then projection of this area in perpendicular direction going to be A dash equal to A cos theta. So we will be considering electric flux through this surface now here is equal to, through this surface, I am talking about this surface, phi equal to A dash into E. Okay, because A dash is the projection of this area in perpendicular direction. So it will be A dash into E. A dash means what? That is A cos theta into E. So phi is going to be equal to, if we use dot product of vectors, E dot A. See what is happening here? Suddenly I have taken vector above the area. Is it possible to get area as vector quantity? Is it possible that volume also a vector quantity? Okay, volume will not think now, although it is also a vector quantity in higher physics and mathematics. Here we will be considering area as vector quantity. But what is the direction of area vector then? Before we proceed here calculating electric flux, let me make that part clear, which you did a bit in class 11 physics course in vector, cross product of two vectors. Suppose there will be two vectors, vector A and vector B. This is A vector and this one B vector. There is a unit normal drawn perpendicular to both vectors A and B. Sense of rotation of this angle with theta. Then you know A cross B, the result of A cross B you did. That A cross B is given by AB sin theta n cap. You understand? You know it very well. You did it before. A cross B is nothing but AB sin theta n cap. So A cross B is a vector which is directed along n cap. Direction of A cross B is along n cap. Okay, why it is so important in discussion of flux? Obviously it is important. Let's proceed. What is the geometrical meaning of this A cross B? Once more, before we start geometrical meaning, let me make this part clear. If we take modulus of A cross B, the result going to be AB sin theta mod n cap. Mod n cap is 1. So it is AB sin theta. Mod A cross B is AB sin theta, as n cap is unit vector, its modulus is equal to 1. So alright. Now let us find the geometrical significance of this cross product. A cross B represent what? For that we will be taking two vectors A and B this manner. Say this is our vector A and this is vector B. Complete a parallelogram whose adjacent sides are these. So this parallelogram is completed. Parallelogram is OA CB. What is the area of this parallelogram? If you draw a perpendicular here, the length of perpendicular, that is BM, is the height of parallelogram. So area of parallelogram will be what? Assume the angle between two vectors with theta, what we have taken here. So this one theta. Now area of parallelogram, area equal to base into height. So OA into MB, that is OA into OB sin theta. You know, OA is what? OA is modulus of vector A, because you have taken A vector this way. It will be AB sin theta. AB sin theta you got earlier, no? AB sin theta here. So area of the parallelogram is mod of A cross B. So A cross B actually represent area of parallelogram, but it is not mod A cross B, it is A cross B. We got A cross B vector as the area, but if we remove the modulus sign, then A cross B represent what? Vector area of this parallelogram. So geometrically, A cross B is the area of the parallelogram whose adjacent sides are vectors A and vector B. Clear? Hope all of you have understood. So area of the parallelogram is A, B, sin theta n cap. We cannot write left hand side without arrow. So area vector coming into existence. Area vector directed along n cap. Alright? Area vector is directed along n cap. Now what is the direction of n cap? Is it the way you have done in class 11 physics? That sense of rotation A to B. Then thumb will give you the direction of n cap? No. N cap will take perpendicular to AB either this way or this way. I mean, n cap if you keep fixed, but area vector is not fixed. Area vector may be this way, I mean along n cap, or maybe opposite to it. So just let me give you one example in three-dimensional space. Imagine this circle lies in xy plane, then area vector, I want to write this area here. That area vector you take perpendicular to it. This time area vector will be along z axis, n cap. So if we want to write this area, it will be area of the circle multiplied by n cap. So area vector is A into n cap. But if you say that no, I will write the area vector by taking unit vector this manner. This is also valid. So that area vector you take this, or A equal to minus A into n cap. Both are valid. It doesn't matter whether you are taking area vector in upward or in downward direction, fixing n cap upward or downward. Okay? But what is the consequence of this thing in electrostatics flux calculation? How to incorporate this area vector in calculating flux? Let me tell you. So this square, yellow one or rectangle, whatever you say, is kept in a uniform electric field of strength E. But this time it is not perpendicular to the direction of flow of field lines. It is bit inclined from the vertical position. So flux will not be same as that when this area was taken perpendicular direction. This white one is perpendicular. This area, if this area is equal to A or A dash, whatever you say, then electric flux phi will be equal to E into this area. But this area and white square and the yellow one, what is the relation between their areas? If we take area of the yellow one as A and area of this one, the white one, as A dashed, then A dashed is projection of A in perpendicular direction, perpendicular to direction of lines of forces or field lines. So A dashed equal to A cos theta. So phi will be equal to E into A dashed. So this implies E A cos theta. Okay. Now this only I have written before, nothing but E vector dot A vector. It is dot product between these two vectors E and A. Theta is the angle between them. If theta equal to 0 degree, let us make some observations here. For theta equal to 0 degree, phi will be equal to E A cos 0. This is maximum. Okay. Maximum flux. For theta equal to 90 degree, phi will be equal to E A cos 90. This is equal to 0, minimum. And for theta equal to 180 degree, that phi will be equal to E A cos 180 degree. This is minus E A, just opposite direction. But this is not mathematics you are doing here, you are doing it for the sake of physics. Where is the physics over there? That area you have taken A as area vector. What will be direction of that area vector? It is perpendicular to this surface. So area vector this time going to be like this in cap. Just little idea of geometry will show you the angle between this in cap and unit normal drawn here, that is also theta. If we have taken the angle between these two equal to theta, then the angle made by this in cap with the field line also going to be equal to theta. Just little bit geometry you apply, you will get this angle is also theta. So what is happening over there? This electric field directed this way, in cap directed this manner at an angle theta with electric field vector. Then phi is equal to E A cos theta. In fact, we will be remembering this formula only by now, that phi equal to E A cos theta. What is theta then? Theta is the angle between unit normal drawn to the plane. This yellow plane was in our consideration, and the electric field vector. Okay. So if you remember that sense, in these three diagrams I have made before I start the class to reduce the timing of this session, you all can imagine there is uniform electric field and this area, circular region area, is taken like this. Unit normal this time directed along in cap only. So phi will be what? This formula we should remember, that E A cos theta or E dot A is the measurement of electric flux and theta is the angle between area vector is what? N cap. So here if this area is A, how to write area vector? I showed you earlier. It will be A into N cap. Angle between area vector. Here area vector is along N cap only. So N cap and A have the same direction. So flux going to be equal to EA cos 0. This is equal to EA. This time is normal by definition. The area vector going this manner and electric field vector is inclined this way. So this angle theta will be considered phi is equal to EA cos theta. Clear? And here field lines are parallel to the surface. So flux is going to be equal to EA cos 90, that is equal to 0. Understood? But somebody asked you in the first diagram, this flux is inward or outward? These field lines crossing the surface, inward or outward? This will help us to calculate outward flux and inward flux. Outward with respect to an observer standing here. I mean this circle area is there, observer standing here, observer O1. With respect to him it is going this manner. Observer 2 standing here, with respect to her, the flux is going inward. And what is the measurement of this flux? Will I say the answer same? No. Now area vector will dominate. Area vector is going to dominate because if the area vector here directed this manner in opposite sense, it will be minus n cap. So let us take here this area vector is minus n cap. I mean unit normal is minus n cap. Area vector this way, but electric field, this one is not changing its direction. E remains this and minus n cap in opposite direction. So what will be inward flux in this diagram which we have taken there? If outward flux phi is equal to E into A, then inward flux is going to be equal to phi equal to this. This is the direction of electric field vector, but area vector directed opposite sense. So it will be E into A cos 180 degree. This is minus E. Clear? So flux this manner it will be phi equal to E into A, and this way it will be minus E. This minus E account for, sorry, this is for n cap, don't be confused. Field lines are going this way only. Okay? So phi equal to minus EA. This will stand for outward and this will be for inward. So for a flat surface, for a plane surface, flux calculation will be done with the help of this formula phi equal to E dot A. What will happen if closed surface is there? Field lines, you can observe uniform electric field. This huge sphere is placed. How to calculate flux through this sphere? We will imagine this sphere divided into infinite number of parts. For every part flux calculation will be there, then we will get total outward flux. Imagine one small area is taken here. Okay? One small area is taken over there. One small area taken here. One small area we are keeping this manner. One small area we are keeping this. These are arbitrary, can lie anywhere. But I have considered these three cases. Why I will explain. So for this area vector, this is a closed surface. One very interesting thing you have to remember. For a closed surface, area vector always radially outward. It will never be inward. So area vector directed this manner. area vector directed this manner, and field vector directed this manner, horizontal direction. It is already shown. So you have to account for this flux. Angle is going to be something which is obtuse. This angle will be theta 1. What is happening for this area here? So that area which you have taken here, let it be delta A1. This area, let it be delta A2. This is radially outward. Radially outward means joining center to this area. It will be directed this manner. Area vector, delta A2 vector will be directed this way, and electric field vector will be directed this way. So this angle also obtuse. What is happening there at this point? If you consider area vector at this point, it will be going this manner. Delta A3 vector directed this way, and field vector directed this way. E. This angle is acute. If we keep a field area, small area here, that is delta A4, then electric field directed this way. So electric field vector and delta A4 vector have the same direction. Now you calculate flux for all these and add not only these four, A2, this is delta A3. You have to add all these. By what formula? This formula is in use, that is phi equal to EA cos theta. So here delta phi 1 through delta A1, we account for this. Delta phi 1 is what? E dot delta A1, which is nothing but this angle we have taken theta, not very clear, but this is theta I have taken here. Okay, I'll make it clear for you. This angle is theta 1, this angle is theta 2, this is theta 3, and this is theta 4. All these to be taken into consideration. You write this as E delta A1 cos theta 1. Delta phi 2 is what? E delta A2 cos theta 2. Delta phi n, E delta AN cos theta. Clear? So net flux going to be equal to del phi equal to sigma delta phi I. Suppose n particles are there, n may be tending to infinity, all these mathematical things are there. I am taking n segments you have divided. N is tending to infinity actually. So this is going to be E dot delta A1 phi I. You write sigma sign over there also. So delta phi I, this is nothing but sigma E dot delta AI. Alright, delta AI vector. Clear? So here also it is I equal to 1 to n, and here n is tending to infinity. That we can write in the form of limit. This is valid when, because the huge sphere you have to divide into infinite number of parts, many directions are there, it's a closed surface, so it is limit n tending to infinity. If we use integral calculus concept here, this phi, don't write delta phi, phi is equal to this thing, that is summation of all those delta phi parts, this is phi total equal to this thing. So phi total or phi out is going to be what? That is integration over the whole surface E dot delta AI. This is called surface integral of electric field. This is surface integral over the whole surface, that's why I've written S. This is surface integral of electric field. Clear? So total outward flux through a closed surface, through a closed curve also. Okay, that we'll solve later. First we have taken this closed surface. Over this surface, total outward flux is given by E into delta AI. What will happen if closed curve is there? This curved surface is there. Okay. For this curved surface, how do I account? It's a problem. Lines of forces are going this manner. How do I account for this? These are three different cases we are discussing. Field lines going this way. How do I account for this? Curved surface. This is not closed one. How do I account for this? How much area these field lines covering if it is placed in uniform electric field? This is a complicated case. I am going to explain in some following example these kind of problems. Before we start that curved surface one, let us solve some simple problem. Inward and outward flux concept already told, and this one has length L, cube of side L, placed in a uniform electric field of strength E. E is the strength of electric field. So you can see that inward flux is there. This is inward, isn't it? And this is outward. Okay, area vector directed this way. This outward flux will be positive, and this inward will be negative. So if you are asked to calculate the outward flux through the surface, phi out going to be equal to E into area. That area is what? L into L. That is E into L square. What about phi in? Let us see this portion. Phi in will be what? Because area vector this time directed this manner. Field vector remains the same. Angle between these two 180 degree. Already I told you phi in going to be equal to E into L into cos 180 degree. That is minus 1. So answer is minus E L square. It comes after that discussion we have already made. It's not a difficult one. And no flux line will pass through this surface, or the surface facing towards me or going away from me, because field lines are parallel to those surfaces. Inward outward means entering here and going out here. So phi out is E into this area, phi in is E into this area. Let us consider this one. Cylinder of radius R placed in a uniform electric field of strength E. The question is, what is the inward and outward flux in this case? See, if this area is R, concept is as similar to the concept we have already discussed. Area is R. This portion area vector is along the direction of the field. Area vector going along direction of field. Am I correct? E vector, A vector same direction. But here A vector going this way. And E vector this manner. I mean that parallel case. Lines of forces are already shown. I did not draw it over there. Alright. So phi in this case, lines of forces going this manner. No, I did not draw. I told already I did not draw it. Wait a minute. So these lines of forces into area, but area vector opposite sense. So phi in will be equal to minus A into E. A is what? Pi r square. This portion area is pi r square. So this will be minus pi r square into A. Here will be what? Phi equal to pi r square into, sorry, not pi r square into A, it will be pi r square multiplied by E. Here it will be pi r square into E. Here it is minus because inward flux, and here it is plus, it is outward flux. Area vector in the same direction. Let us see this one. Cone of radius are placed in uniform electric field of strength. Complication starts from here. Because field lines in the previous two examples were going parallel to these curved surfaces here. It was not a problem at all then, because those lines of forces running parallel, they not create any flux for this one, like this. Here also along the curved surface no flux linkage because electric field directed that way. So how do I account for this? Here it is going through these two only. But in case of cone, what will you do? Because it is intersecting this curved surface also, then what to do? You remember, this time we take projection of the curved area at the end. There is the end cap, area of the end cap. So the projection of the curved area will be lying here only. So phi in this case going to be what? Phi equal to pi r square, that area, into strength of electric field. We will be considering this portion only. Understood? Projection here only. Okay, area vector perpendicular to the surface. This is area vector I am drawing. Everywhere area vector remains the same. That is along the direction of field line. So phi equal to pi r square. Yes, of course, phi in is there. This is phi out. Really field lines are entering. So phi in will be what? Just opposite of this. We need not calculate this. So it will be minus pi r square into E. Why we did not calculate? Because already told this projection area is the area to be taken into consideration. So flux lines, I mean lines of forces entering means they are entering this curved line. Clear? Now the most complicated case here I am going to discuss with you when the cylinder stands straight. Curved surfaces are facing electric field lines. How many lines of forces will pass through it? It's a complicated case. So what to do? Again we go by, for curved surfaces, we go by the concept of effective area. I mean projection of the area, curved surface area, which is facing the electric field line perpendicular. I am showing you this is three-dimensional concept, drawing it in 2D. So you have to keep your patience here. I hope you don't have any problem in understanding that this plane now, this plane I have drawn here, this plane is perpendicular to direction of field lines. If this has radius r and height h, this height is h and radius r, then flux linkage, I mean flux inward, phi in, will be equal to RH, and strength of electric field is E. This will be minus E. I mean minus ERH. Because we have considered this area only, field lines and area vector opposite. Field line going this manner, area vector going this manner. That's why minus. And phi out will be RH into E along the direction of field lines. So it will be simply ERH. Hope all of you have understood. You can try sums from your textbook as well as from H.C. Verma, Irodov or Resnick, Halliday and Crane. This concept will help you a lot to solve JEE problems also. A few more complicated cases are there. Example 5. Uniform electric field, this much Newton per coulomb. You all can see that 4i, 5j, 3k exist in a region. Calculate flux of electric field through the surface bounded by the following curves. So what I am going to do there, position of these circles will be finding here. If I have taken this one x-axis, y-axis, this one z-axis, then the circle lying in xy plane, first one, radius of this circle is equal to 5. So phi equal to area vector. Let us write area vector first. Unit vector along z axis, you know, k cap. This is I cap and this is j cap. So area vector, it is normal to the surface, and you can see that it is directed along positive direction of z axis 3k. So this field, I mean Ez equal to 3k lying along z axis. Area vector, this is pi r square, that is pi into 5 square. This is also lying along z axis. So it is 25 pi k cap. Phi going to be what? Phi out. You can, out means radially outward. Phi out is going to be equal to 25 pi k dot 3k. E dot A or A dot E, same thing. A dot E I have taken. So 75 pi k cap dot k cap. Dot product of these two vectors is 1 only. Mod k cap square, that is 1. So it is 75 pi Newton per Coulomb meter square. Done. Phi out. Phi in will be what? Phi in means this field line is going outward. So phi in will be minus 75 pi Newton meter square per Coulomb. Clear? Now this plane that I am doing the third one, because second one you will be trying at home. X square plus z square equal to 4. So for this circle, x square plus z square equal to 4, it lies in xz plane. The radius of this circle is equal to 2. You write the area vector here and the field vector. Field is directed in what direction? We need field along y-axis. What is its value? 5j. So E is equal to 5j. This field only along z-axis. So 5j, and area vector is what? It is pi into 2 square j cap. 4 pi j cap. So phi out means it is going along positive y-axis. Dot product of E and A. Just calculate these two. Is 5j dot 4 pi j, that is 25. J dot j is 1. So answer is 25. Alright. Hope you have understood. This is E equal to EXI, EYJ, EZK exist in a region. Cube of side A is placed with one vertex at the origin. They stated this part is origin. And 3 edges along direction of coordinate axis. This one y, this one x, and this part is z. Name these vertices also. This is A, B, C, D, E, F, and G. Calculate the flux of electric field through each face of the cube to earn total flux. Very easy. If you have understood our previous sums, then you can do it yourself. So how many faces are there? 6 faces are there. Let me start considering this one first. That is face along y-axis. So along y-axis, what is there? two faces are there. One is OAFC. So phi in going to be what? Fill in that direction along y-axis is this part. And length of each side is A given. So area of each side is square. A equal to A square. So here phi in is along the direction of electric field, because electric field given this way. So here phi in going to be negative again. Phi in equal to what? That is, sorry, EY, not EX. This is EY into A square and y minus 1. This I have explained. Minus EY A square. Phi out. Phi out means through which surface? DBEG. This is EY into A square plus 1. This is outward. Outward flux is positive. Okay? So this is plus. What is going to happen along Z axis? Along Z axis, phi in will be what? Electric field line entering here and going out here. The same manner. This component along Z axis given EZ. So phi in will be EZ into A square minus phi out EZ into A square plus. They get cancelled. No, cancel or not, that I am going to tell you. Let us write along x-axis what is happening. Along x-axis what will happen? Entering through this ECOB and coming out through FADG. So phi in again minus EX into A square. Phi out through the surface FGDA. This is given by so flux through all 6 surfaces we found. And is this sum 0? Yes, quite obvious. They're getting cancelled. So answer is 0 only. Total outward flux was the requirement of the problem through the cube. So phi net is equal to 0. Clear? So if you keep a cube in uniform electric field, total outward flux through it will be equal to 0. It's a textbook problem. Please go through. No IDG. Textbook. Ordinary question. And this is the explanation. Clear? This time problem is bit complicated here. Uniform electric field. See, it is varying. 2x I cap, 3y j cap, 5z k cap. Changing. Unit cube is taken here. Your problem is to calculate flux of electric field through each surface. Again we name O, A, B, C, D, E, F, G. So this is at the origin. We have taken 0, 0, 0. This is your y-axis. This one is the x-axis. This one the z-axis. So this point B has coordinate 0, 1, 0. Quite obvious. D has coordinate lying in xy plane. So z coordinate 0, 1, 1, 0. It is lying in space. Its coordinate is 1, 1, 1. Along z axis 0, 0, 1. This is xz plane, y is 0, 1, 0, 1. And this one is the yz plane, x coordinate 0, 0, 1, 1. Clear? All vertices are there. But here electric field is changing. See, along y-axis if we take into consideration, it is minus 3y. So it means when you consider along y-axis this face and this opposite face is there, electric field value here y is 0 because this is connected to the origin. So here EOY equal to 0. But electric field at P along y-axis is not 0. What is its value? Minus 3y. What is the value of y here? That is 3 into 1. It is minus 3. So here EBY is minus 3. So if you just calculate along x-axis, then phi in equal to 0. Phi out will be what? Minus 3 unit cube. So area is 1 Newton meter square per coulomb. What is the significance? The significance is that electric field is directed right to left. So this is for inward flux. That's why it is negative. But outward flux is 0. Here we cannot decide this. Clear? Let us do one more case. That is along z-axis. Along z-axis it is 5zk. But here field lines are entering and here field lines are going out. Isn't it? What is the value of field line here? Z is equal to 0 here. So EOZ equal to 0. And here ECZ is 5 into 1. Because Z is equal to 1 over there. 5. So what is phi in here? Phi in is 0. Phi out will be what? That 5 into 1 square Newton meter square per coulomb. Similarly, let me calculate phi for this we did first one along y-axis. This is along z-axis and this one along what? Along x-axis. This is along x-axis. Along x-axis it will be what? Along x-axis field is 2x. So x-axis means this way. On the face OBEC, electric field along x-axis is 0. And on this face FGDA, the electric field EAX equal to what? That is 2x. 2 into 1, that is 2. So phi in along x-axis is 0. Phi out is going to be equal to what? Phi out is going to be equal to 2 into 1 square Newton meter square per coulomb. See, if we count for net flux here, 2 plus 5, 7 minus 3, 4 not equal to 0. So net flux through the cube may not be equal to 0. Why it is not 0? Because non-uniform field. In a uniform field, it will be 0. It will enclose no charge. Here it will enclose some charge. Why? Wait for the next session I am coming with, that is on Gauss law. Thank you.